In 20 through 38, determine whether the statement is true or false. Justify your answer with a proof or a counterexample as appropriate. In each case, use only the definitions of the terms and the assumptions listed on page 161, not any previously established properties. The difference of any two even integers is even. Now, upon initial observation, you might notice that the statement is true. If we take two even integers like 8 and 6, then the difference is even, which is 2. That's true. If you do 26 and 14, the difference is 12, which is even. That's true. And you can keep checking to verify that this statement is in fact true. So let's try to prove this statement is true. Now, this is a universal quantification on two even integers. And then this statement makes a claim about the difference between those two even integers. Let's first instantiate two even integers. So let m and n be two even integers. The first thing we could do with this assumption is we can unpack what it means for m and n to be even integers. So that means m equals 2k for some integer k by definition of an even integer. And we could say similarly, n equals 2 times, we can't use the variable k again, or else we would be assuming that m and n are the same numbers. And that might not be the case. We might be picking two different even integers. So instead of saying n equals 2k, we'll say n equals 2 times j for some integer j. It doesn't matter what letter we use so long as we don't use the letters that are already instantiated like m, k, or n. Now this is the point at which many students get stuck because they start with the assumption and then they unpack the definitions within those assumptions. And from those definitions, it might not be clear that the conclusion is true. So how do we reach our conclusion from here? Well, the claim that's being made is that the difference between these two even integers is even. So let's investigate the difference between these two integers. So the difference would be m minus n, or n minus m, it doesn't really matter, or the absolute value between the two. I'll just pick n minus n because this proof will be symmetric at the end anyways, so it won't matter. Now, m minus n is equal to 2k minus 2j, and that's by substitution, which is one of the assumptions listed on page 161. Now, the goal is to show that this difference is even. What does it mean to be even? It means that we can rewrite this statement. That means we can rewrite m minus n as 2 times some integer. We're almost there, actually. Notice that 2k minus 2j is 2 times k minus j. Now you can clearly see that m minus n is 2 times some integer. This is by algebra, which is one of the assumptions listed on page 161. Since integers are closed under subtraction, that means k minus j is an integer. So it equals s for some integer s. So now we've established that m minus n equals 2 times s for some integer s. That means, by definition of even integers, m minus n is even, meaning that the difference between these two arbitrary even integers is even. So if m was 12 and n is 8, then we can use this proof to establish that 12 minus 8 is even. But since m and n are arbitrary, this means that the difference of any two even integers is even. Not just specifically m and n, but any two even integers. It doesn't matter what m and n are because m and n were arbitrary even integers. It is the arbitrariness of these two instantiated variables that allows me to justify a universally quantified property. Thanks everyone, and I'll see you in the next video.